Hi, welcome back to Test Science's series of Reliability Growth Modeling modules. In this module, we will go into detail about the Poisson distribution. Recall that in Module 3, we covered the basics of probability density functions, or PDFs, and cumulative distribution functions, or CDFs. Each distribution has a unique probability density function that has parameters and assumptions, both of which we will go through for the Poisson distribution. The Poisson distribution is extremely important in developing reliability growth models. So let's begin by thinking about a particular scenario. Suppose we want the probability density function for the number of cars that pass by your house during one particular week. Let's think about this time interval as being comprised of many smaller time intervals. So for instance, here on Sunday, I have it from 0700 to about 1100. And these things are called subintervals. Let's make each subinterval so small that at most one car could pass by with a probability greater than 0. Okay, so let's look at probabilities within these subintervals. So recall that we said that each subinterval contains the event of one car passing by. So the probability that one car passes in that subinterval is equal to p. And the probability that no cars pass by in that subinterval is 1 minus p. And because of our assumption, the probability that more than one car passes by in any subinterval is 0, because we said that subintervals only contain an event of one car passing by. And because each subinterval only contains one car passing by, whether or not that actually happens, then the total number of cars that pass by your house in a week is just the total number of subintervals. So say on Sunday we had 6 subintervals that had a car actually pass by, and 4, 5, 5, 4, 7. Then the total number of cars that pass by your house in a week is just the total number of subintervals that have one car passing by. So we haven't formally covered the binomial distribution, but we have set things up to use it to derive the Poisson distribution, since we actually used it in Module 3, the PDF and CDF module. Now, recall that for a binomial distribution, we have some experiment going on, and for us, we're looking at cars driving by. And it has some fixed number of trials, or subintervals, which we've denoted as n. And each trial independently results in one of two outcomes. So within a subinterval, we could have car passes by or doesn't. We have some binary outcome. And when we say independent, we mean that one trial, say this trial or subinterval, does not affect the result of the next. So the probability of a car passing by is the same for any of the subsequent subintervals or trials. And when we set things up this way, the expected number of cars we would see drive by is n times p, where n is the number of subintervals and p is the probability that a car passes by in that subinterval. So now returning to our car counting example, the last thing we said was that the total number of cars that pass by your house in a week is just the total number of subintervals that have one car passing by. And your best guess of the number of cars that will pass by during the experiment is n times p. Well, suppose that we make more smaller subintervals while maintaining the total length of the test. So for us, we were looking at 1 week. So we're maintaining the length of the test, but we're making more n. In other words, we are divvying up the week into more and more subintervals or trials, and even smaller n. So small, in fact, that the probability of one car passing by in any of these subintervals goes down as the number of subintervals goes up. So we can write this as n goes up, the probability of success, or in our case, the probability of a car actually passing by in one of these really tiny subintervals, goes down. Now, formally, the Poisson distribution is derived as the limit as the number of subintervals goes to infinity But what does this mean really? Well, the binomial distribution gives us a way to estimate the probability of success or failure for an event for n trials or test runs. And the Poisson follows the same line of logic. So as n goes to infinity, our increments are so tiny, they're really, really tiny, and the probability of a single event goes down. So the binomial converges to a Poisson when we are interested in some random event in which the probability of any of the individual events occurring in n trials or subintervals is very low. So we can visualize this as so. So let's say that we observe 5 cars passing by in our week of observation. Now, since each subinterval does not contain the possibility of more than one car passing by, let's hypothetically say that those 5 cars pass by in these 5 subintervals. Now, should we increase the number of subintervals in our week, we are still maintaining the overall length of the test per se. We're still maintaining that it's 1 week. And the overall count also remains the same because we're maintaining this 1 week count. But there will be many more subintervals where a car does not pass by. So it contributes 0 to the count of cars we observe in a week. So the binomial distribution ends up converging to the Poisson, where the Poisson utilizes one parameter, lambda, which is equal to n times p, the expected value or mean. But we'll go into detail on that on the next slide. But essentially, the Poisson simplifies the calculations through one parameter as n gets very, very large. So large, in fact, that the probability of any one car or event happening is very small. So I'll save you the complicated derivations, but what we get is this particular PDF for the Poisson distribution, where the PDF is e to the negative lambda times lambda to the x all over x factorial, where x ranges from 0 to n, the number of trials or tests that we're interested in. And lambda is some positive rate parameter. And lambda, in fact, is the only parameter associated with the Poisson distribution. And you can think of it as equal to n times p, which recall n times p was the expected value of x in the binomial case. Now, the Poisson distribution is a distribution on counts. And remember, we derived it as the distribution for the number of cars that would drive by in a period of time. Can you think of any other examples that would be modeled well by a Poisson distribution? Well, what about accidents in a given unit of time? What about people walking into say, a local store? Maybe the number of telephone calls handled by a receptionist in a time interval. And maybe even the number of typing errors you make when writing an op-ord late at night. But can we think of an example that relates specifically to reliability growth modeling? Well, yeah, what about system failures? If we're interested in counting the number of times the system fails during a time period of testing, then that surely too can be represented by a Poisson distribution. But before we walk through a specific example, let's formally define some characteristics of the Poisson distribution. So if x is a random variable possessing a Poisson distribution with the rate parameter lambda, then the expected value of x is equal to lambda, which intuitively makes sense because we said in the binomial case this would be equal to n times p. And the variance of our random variable is also equal to lambda, which is n times p. So now we're ready to walk through an example to understand how the probability function works for the Poisson distribution. So let's return to our car watching example, where we are observing a car for 1 week. And let's say it is theoretically known that the mean number of cars that pass by your house in 1 day is 3. But we want to know the probability that we observe 10 cars in a week. So first, we're given the mean for 1 day. But we need the mean for 1 week in order to use the probability function correctly. So here, the mean or expected number of cars that will pass by in a week would be 3 times 7, or 21 in a week, because you have 7 days in a week. Now the question we asked is, what is the probability we observe 10 cars in a week? Thus, we are solving for probability that x equals 10. Or in our case, you can just write probability of 10. And this, using the probability function on the previous page, is just e to the negative lambda times lambda to the x all over x factorial. And this is for, not y, x greater than or equal to 0 and lambda greater than 0. Now, using the given information that lambda is equal to 21, we can simply plug it in to find the probability of interest. So here we would have e to the negative 21 raised to 10 all over 10 factorial. And this comes out to 0.00348. But why is this so small? Didn't we say that we expect 21 cars in a week? So surely 10 is less than 21. Shouldn't we feel confident that we observed 10 cars? Well, yes, but the probability we found was that we observed exactly 10 cars when the mean is 21 for a week. So maybe a better question is asking, what is the probability we observe at least 10 cars in a week when the mean is 3 cars per day, or 21 per week? And this is simply written as the probability that x is greater than or equal to 10. And this is actually the sum of I equals 10 to infinity of our PDF, so our probability function for the Poisson distribution. So e to the negative lambda times lambda raised to the x all over xi factorial. And we do this because by the definition of a probability function, the probabilities must add up to 1. Thus, we add the probabilities from 10 to infinity to get the joint probability of observing at least 10. Or equivalently, we could write this as 1 minus the probability that x is less than or equal to 9. Now, this is a long and tedious calculation, but using software like R or available tables, this calculation actually comes out to 0.997. And this seems to align with our intuition that we would obviously observe at least 10 cars when the mean is 21 in a week. Now, on the other hand, if we looked at the probability we observe more than 21, so more than our mean, it actually comes out to 0.529. So it's basically up to a coin toss if we observe more than the mean for this problem. So using these past two examples, we've demonstrated that the Poisson is a very useful distribution when we're interested in the probability of counting event occurrences. But now consider this. We've really only been talking about one test run, 1 week of observing cars. Normally in an experiment setting, we would want to run multiple tests per se. We may even be interested in looking at time intervals. Now, where are we going with this? Well, what we covered in this module are the basics of the Poisson distribution, including the probability distribution function, assumptions related to the distribution, and the one parameter lambda. And this gives us a method for dealing with time intervals, where we are counting events and determining the rate of these events happening. The next module goes over counting processes, which broadly covers this concept of counting events up to some point in time of our test. So we may want to do a check-in midweek or halfway through some sort of test.